It's a pleasure now to introduce Melissa Liu from Columbia University, and she will be talking to us about topological recursion and the Crepant Transformation Conjecture. Melissa?
Thanks a lot for the introduction. It is my great honor to have the opportunity to speak at this geometric festival. I wish to thank the organizers for the kind invitation. The title of my talk today is Topological Recursion and Crepant Transformation Conjecture. This is based on joint work with Bohan Fang, Zhengyu, and Zhengyu Zong. Let me start with explaining what the Crepant Transformation Conjecture is. So we will consider X plus and X minus. Each of them can be a smooth complex algebraic variety, in particular a complex manifold, or a smooth Deligne-Mumford stack, and in particular, it is a complex orbifold locally isomorphic to the quotient of Cm by the holomorphic action by a finite group G. In this talk, Kx plus minus will denote the canonical line bundle instead of the canonical divisor. It is the topic exterior product of the holomorphic cotangent bundle. If X is a smooth algebraic variety, it's an algebraic line bundle. If it's a smooth orbifold, then in general, it is an orbifold line bundle. We say X plus and S minus are K equivalent if there exists a smooth variety or a Deligne-Mumford stack Y, and birational maps F plus minus from Y to X plus minus, such that the pullback of their canonical line bundles agree on Y. So in this diagram, F plus and F minus are defined everywhere on Y. The inverse map of F plus and F minus are defined on a dense open subset. The birational map between X plus and X minus is called a Crepant transformation because there is no discrepancy between the pullback of their canonical line bundles. The Crepant transformation conjecture was first proposed by Yongbin Ruan around 2001, which is 20 years ago. It has been refined and expanded by many authors in the past 20 years. This is an incomplete list. It has many different formulations, but in general, Crepant transformation conjecture relates Gromov-Witten invariants of X plus and X minus. Gromov-Witten invariants of X are virtual counts of parametrized holomorphic curves in X. Today, we will focus on a very special case where our targets are symplectic toric Calabi-Yau 3 orbifold. In this talk, the Calabi-Yau condition is simply saying the canonical line bundle is a trivial holomorphic line bundle. To define Gromov-Witten invariance, we do not need the structure of a Ricci-flat Taylor metric. So next I will describe the basic geometry and topology of symplectic toric Calabi-Yau 3 orbifolds. And then I will define their Gromov-Witten invariance. Let G be the p-dimensional complex algebraic torus. And we assume that it acts on the p plus 3-dimensional complex vector space linearly and faithfully. The action can be diagonalized, and it's simply given by p plus 3 characters of G, called rho I. We want the quotient to be Calabi-Yau, so the product of rho I is a trivial. The action of this G restricts to a Hamiltonian action by the compact torus GR, which is a p-dimensional compact torus, U1 to the p's power, and where Cp plus 3 is equipped with the standard symplectic structure, which is also scalar. And the moment map of this Hamiltonian action by GR is determined explicitly by these characters, rho I. Now, suppose that we have theta, which is a regular value of the moment map. So if the GRX freely on mu inverse theta, the quotient is a smooth manifold equipped with a symplectic form omega theta coming from the symplectic reduction. More generally, we also consider the case where GR can have finite stabilizers. In this case, we have this bracket which stands for the static quotient. This static quotient is a symplectic toric Calabi-Yau 3 orbital, where the symplectic forms omega theta comes from the symplectic reduction. We also have the coarse moduli space, which is the underlying topological space of the set of orbits. It is also a complex algebraic variety, which is the GIT quotient of Cp plus 3 by the complex algebraic torus G, where the stability condition is given by the theta. So this coarse moduli is a simplicial toric Calabi-Yau threefold. When the action of GR on mu inverse theta is 3, then the curly x theta is the same as x theta. It's coarse moduli space. Let me give you a simple example. Suppose that let's C star acts on C4 by weight 1, 1, 1 minus 3. The moment map is given explicitly by this. The regular value of the moment map are just non-zero real numbers. If theta is greater than 0, then the preimage of theta, in the preimage of the theta, Z1, Z2, Z3 cannot be all 0. The action of C star is free, and the quotient is the total space of the canonical line bundle over P2. When theta is less than 0, the force coordinate Z4 cannot be 0. We can use the C star action to scale Z4 to 1, and we see that this is the same as C3 mod Z3, where Z3 is embedded in C star as the group of cubic roots of unity. So in this example, when theta is greater than 0, we get a symplectic toric Calabi-Yau 3 manifold. When theta is less than 0, if we take the static quotient Z3 mod Z3, we get a symplectic toric Calabi-Yau 3 orbifold, and its coarse moduli space is the simplicial toric Calabi-Yau threefold. And in this case, x plus and x minus are related by Crepant transformation, and they are also related by a single wall crossing, toric wall crossing. And Kp2 is the toric Crepant resolution of C3 mod Z3 obtained by blowing up the origin. Crepant resolution conjecture in this particular case should relate the Gromov-Witten invariance of Kp2 and C3 mod Z3. Before defining Gromov-Witten invariance, I need to introduce the notion of orbifold Chen-Ran cohomology. So first I need to introduce inertia stack. This inertia stack can be defined for more general stacks, but today we will just give the definition in our special case. So let U denote the set of semi-stable points determined by theta. So X is equal to the quotient mu inverse theta by GR and also U by G. And curly X is the stack quotient. So, so in our case, G is an abelian group. So we will define the inertia stack also as a global quotient. So we take the subset of U cross G, which consists of pairs V, comma B, where B is a point in U fixed by the element B in the group G. And the G acts trivially on the second factor G. And the action of the first factor U is the same. And we can see that if the action is free, then B must be the identity element, and then we just get back to X. In general, in our case, it will be a disjoint union of connected components labeled by a finite subgroup capital B of our group G. Here, this capital B is the set of elements in G such that the fixed point set of B is non-empty. And so the connected component associated to this a little b in big B is just the quotient of the B fixed point in U by G. And there's a component H, you can associate the H. So basically this is determined by the eigenvalue of the action on the tangent space. And in our case, it will be integer 0, 1, or 2. So I will just define Cherang cohomology as a complex vector space, as a graded complex vector space. So you just take the usual cohomology. So if you consider the complex coefficient, so the singular cohomology is just the cohomology of the underlying space. So you take the singular cohomology of each of this xp with complex coefficient, and you just shift the degree by this h. And then in our case, so x is a toric Calabi-Yau 3 orbifold, and you will get h0, which is one-dimensional, h2 and h4. Yeah, if x is smooth, these are just the usual cohomology. And it turns out that the dimension of h2 will always be t, which is the torus G you start with the quotient, and the dimension of h4 will be less or equal to t. So we will call it mass graph, which will appear sometime later. So let me give you an example. It's these 3 mod these 3. So these 3 will, so here this action is not free, and the group is still finite. So this capital B is just these 3 itself. So you have this x naught, which is x itself. And for the other 2 non-trivial elements, the only fixed point is the origin. So the other component are called the twisted sectors. So in this case, those twisted sectors are just point mod these 3, which is the classifying space of these 3. But if you consider cohomology with complex coefficient, this is the same as a point. And one compute the h things like zeta x by eigenvalue zeta. So we compute the h and we get 1 and 2. So we get the Cherang cohomology of C3 mod Z3. So if you don't do the Cherang cohomology and you just get the cohomology of a point, which is one-dimensional, but this Cherang cohomology has contribution from the two twisted sector, and you have H0, H2, and H4. So on the other hand, we know that so this C3 mod Z3 is related to KP2 by Crepant transformation. And we of course know that the usual cohomology of KP2 is the same as the base P2, which is three-dimensional and also has like H0 and H2 and H4. Actually, this is a more general phenomenon. So today we will only use the structure of Cherang cohomology as a graded vector space. There is a top product, but we will not use it. So in general, if you have two toric Calabi-Yau threefold related by a single toric crossing, where KP2 and C3 mod V3 is just, sorry, this mu3 should be V3. So this is an example. Then it's always true that they are the same as graded vector space. Okay, so now with this preparation, we are ready to define Gromov-Witten invariants. So there are more general Gromov-Witten invariants, but today we are going to define the following. So consider the second Cherang cohomology. In general, it has contribution from both the untwisted sector, which is P prime dimensional, and twisted sector. So the whole dimension is P. And then we are going to define something as follows. So this is some correlator which will be some Gromov-Witten invariants. So there's a genus G and degree D prime. And we also take L element from the twisted part of the second Cherang cohomology. So what are these? So this correlator is supposed to be the virtual number of holomorphic maps F from a nodal orbifold curve of genus G to X. If we forget about the orbifold structure, this is just a smooth curve or curve with at most nodal singularity. And we allow orbifold structures at the mark point x1 to xl or at the nodes. And for each of the mark point, it is like a stacked point with where the automorphism group is finite and strictly. So this D prime, so in this correlator, so I already explained like G is the genus. If you forget about the orbital structure, this is just the genus of the possibly nodal curve. And also, if you consider just the underlying space, it has a curve class D prime, which is the second homology class of the target. And finally, so when you have this stacked points, and the stacked point has the automorphism group is generated by this beta, and under F, the image is a point in the inertia stack, and we require that this point lies in the connected component associated to Dij. So it turns out that there's a way, in general, if you consider moduli of such maps, it's actually a singular orbifold. But it's actually virtually smooth in the sense that it doesn't have, it's a singular, it doesn't have a tangent bundle, but it's a virtual tangent bundle, which is the difference of two vector bundles. And actually, because of the way we set up, because of the Calabi-Yau and three-dimensional and all this insertion, this virtual tangent bundle has rank 0. So this moduli space is like a virtual manifold of dimension 0, actually virtual orbifold of dimension 0. So this virtual number is supposed to be number of points, and because it's an orbifold, so the virtual number is a rational number. So these are the Gromov-Witten invariants. So yeah, so of course there are a lot of like foundational work that goes into this definition. Moreover, because of the target is actually non-compact, we will need to use the torus action to define this invariance, but it can be defined. And this FG is just the idea is just a generating function of this genus G when we fix a G and sum over all degrees. So finally, sorry, the last line is to say that when we are in the smooth case, then you don't have anything from the twisted sector. So you don't insert anything. So and the extended degree is the usual degree. And then what you get in the smooth case is for each genus in each degree, you get the Gromov-Witten invariant. And this FG is just a generating function of all genus G Gromov-Witten invariants. And so the number of the component of the degree is the same as the dimension of H2, which is P. So you see that when we cross the wall and get to some orbifold, then we have fewer curve classes. For example, if in the KP2 case, so in the KP2, so we know there's 1 degree for KP2 because H2 of KP2 is 1 dimensional. But you see, when you cross the wall and you get to this orbifold, it's T3 mod V3. So any holomorphic map on this compact Riemann surface to C3 mod V3 is just a constant. So we need this twisted sector to extend the degree so that this generating function will have the same number of variables after we cross the wall, and there's some hope to identify their Gromov-Witten invariants. Yeah, I hope this. So any questions? Okay, so then the next thing I will discuss is something similar to this, but this is the open version. So this will be the virtual console parameterized holomorphic curves in X, but we allow the curve to have boundaries in Lagrangian submanifold, more generally suborbifold in our symplectic toric Calabi-Yau 3 orbifold. So the Lagrangian that we will consider is called F90 Lagrangian. They are actually generalization of Calabi-Lawson special Lagrangian in C3. So recall that what this Calabi-Lawson special Lagrangian in C3 looks like. So one example you can it's given like explicitly by this equation. So I can draw a picture. So the picture in the middle is C3 with the 3 coordinate axis. So where each axis is a copy of C. So then this Calabi-Lawson special Lagrangian in this particular example is, it's diffeomorphic to a circle times R2, and it intersects the V1 axis when V2 and V3 are 0, then V1 has norm 1. So it intersects the V1 axis along the unit circle, and it found the holomorphic unit holomorphic disk in the V1 axis. So the open Gromov-Witten invariant should count this holomorphic disk and covers of this holomorphic disk. So now on C3, so C3 is a Taylor manifold, and there's a moment map whose image is in R3, and the image of the moment map is the first octane. So now you can consider the 2-dimensional subtorus, the compact Calabi-Yau torus. So this is the subtorus which acts trivially on the canonical line bundle at the origin. And then like this compact, the moment map of this compact Calabi-Yau torus is obtained by project the 3-dimensional moment map to R2, and then it becomes surjective. So here you see that I draw like 3 lines, which are the image of the moment map of the three coordinate axis, and under this, in the under the three moment map of the three-dimensional torus, the image of the Lagrangian is a ray. But then when you project to this plane, it just becomes a point, and in this case, it's 1, 0. Yeah, so this is in C3. So in general, yeah, so if you have smooth toric variety, this Agnacci-Vafa Lagrangian, which looks exactly like this. So it is contained in some, so in general, smooth toric varieties of dimension 3 are obtained by gluing C3 charts. And this kind of Lagrangian is always contained in one chart. And it intersects a one-dimensional orbit, which is the copy of C star along a circle. So the picture looks like the C3 case when your target is actually smooth. More generally, because now we allow toric Calabi-Yau 3 orbital, right? So then we have the generalized version of this. So in general, this Agnacci-Vafa Lagrangian in the orbital case will still intersect some one-dimensional orbit. But now this one-dimensional orbit can be like C star with the action with like generic stabilizer. So it's like C star with a trivial action by a cyclic group of order n. So it's just like C star. So C star is like a cylinder, right? I draw this black cylinder, which is C star cross BVM. So it's a stacky C star. And then this Lagrangian is like S1 times C mod all the action with Cm by rotation. So after you quotient, you get this cone singularity of angle 2 pi over m, and then you have this singularity over S1. And then this L and this stacky C star intersect at the stacky circle. So this is the more general Lagrangian in our case. We will just consider this kind of very special Lagrangian boundary conditions. And in particular, this Lagrangian boundary condition is nice in the in two aspects. First, we can still get zero-dimensional moduli space, and we can still define and compute the torus localization. So now, again, we will, this correlators is, again, so now the correlators will count holomorphic maps from Riemann surface, possibly with orbital point, possibly with boundary, and possibly with nodes to X. So, so it's for the Riemann surface of genus G with M boundary circles R1 to Rn. So in the picture, there are 4 boundary circles. So we require the boundary circles to be smooth. And we can allow orbital points at the mark points x1 to xl. And if there are nodes, and you can also have orbital structure at the nodes. So now, because of the border Riemann, so previously, so we have topological type of the domain, which is given by the genus G. Topological map type of the map is given by degree, or more generally, extended degree. Now, because of this boundary, we also have this winding numbers. So you see that, like at the mark point, we still require that the evaluation map of U takes value in the inertia stack. We still require that it lies in the kinetic component associated to this element Vij. So this explains the dependence of the correlator, and also G is the genus. And but now, because this boundary circles is mapped to L, so it represents element in the fundamental group of L. But now the fundamental group is homotopic to a circle times the classifying space of Vm. So the fundamental group is isomorphic to V cross Vm. Since it's abelian, it's the same as H1. So this mu I are the winding numbers of like the circle Ri, like the numbers of the circle Ri, like covers the circle inside this L, and also there's this Ki, which is an element in Vm. So we have this winding number, and I would maybe say holonomy Ki, Vm holonomy, and also finally, so now the degree should be a relative homology class. But then because you see, because now L, we can always find a like possibly stacking holomorphic disk bounded by this L, and this alpha is some relative homology class, and so the relative homology class is given by an absolute homology class plus a multiple of alpha, where this multiple is determined by the winding numbers. So in any case, it's just because we know it's just previously we can insert these correlators and it depends on genus and degree D prime. So now because of the boundary, we have like more topological data like winding numbers mu I and the holonomy Ki. But in any case, we can fix the topological type G and N of the domain, and we sum over all the possible degree and winding numbers. So now we need more variables. So recall we still need one variable for each of the extended degree. So we have, so these are the, so I will call this a model full string coordinates. So we still have this dependence. So we still have this dependence on tau, which keep track of the P like extended degrees. And but now we have like this winding numbers. So we have this x1 tilde to xn tilde to keep track of the winding numbers. And also we have this discrete thing K1 to Kn in V mod M3. So to keep track of this, it will be convenient to, so we don't have this when our Lagrangian is actually smooth. When our Lagrangian is stacky and contains a circle with generic stabilizer Vm, it is convenient to introduce this complex vector space to dimension M and introduce some basis Ek. And then we can like sum over all this. And so we get this FGN, which is a vector valued vector valued function, which takes value in the nth tensor product. Yeah, so basically this is a vector value function. Right now it's just a formal power series. A priori it doesn't converge. It doesn't, sorry, a priori it doesn't converge. It's just a formal power series in like exponential tau A for the first P prime, and also tau A for the from P prime plus 1 to P. But basically it's vector valued formal power series, and it just it's a generating function for all the open Gromov-Witten invariants of all possible topological types of the map when you fix the topological type G and N of the domain for the Riemann surface. So now these are the open and closed Gromov-Witten invariants we consider. Yeah, I hope geometrically it is clear. So again, because of this, when we have these correlators, so all this condition guarantees that the moduli of such maps is virtual dimension 0. So we can define virtual number, which is again a rational number because these are This moduli space are orbifolds. Oh, but there's this under this picture of the border Riemann surface, I said counts depend on the framing F in Z. So this is just some extra data which you need to get some well-defined number, because now this moduli spaces are like in the best case manifold or orbifold with corners. Right? So it's like intersection theory is not so well defined, so we need this kind of framing to impose some boundary condition and get a well-defined number. But in any case, this generating functions can be defined. So next, so in the rest of my talk, I will first like review some known results about the Crepant resolution conjecture in terms of this generating function, and then I will stay on new results. Yes, so for toric Calabi-Yau 3 orbifolds, Coase-Witten and Zhang in 2014, so it proved genus zero equivalent Crepant transformation conjecture for a K equivalent toric dilemma for stack X plus X minus related by a single toric wall crossing. Their result is very general, so their X plus and X minus can be any dimension and it can be non-Calabi-Yau. So if you specialize their more general results to the toric Calabi-Yau 3 orbifold, their results will give some relationship between F0, generating function of genus zero, Gromov-Witten invariants. Okay, so earlier, so Zhengyu, so he considered this particular target, which is given by the following. You consider the VM action Z2, where you identify VM as the mth roots of unity. It acts on Z2 by the opposite weight. The quotient is known as the AM-1 service singularity. So this we consider toric Crepant resolution, and also the static quotient, and we just cross it by C. So X plus and X minus are related by Crepant transformation conjecture. So in this case, Zhengyu, so in particular we can define this generating function fg of Gromov-Witten invariance. In this case, you have m minus 1 twisted sectors, right? Because there are m group elements, and so Zhengyu showed that so the fg of x plus and x minus are related by analytic continuation and change of variables. So this is true for all genus. And a few years later, Dusty Rose generalized this result to toric Calabi-Yau 3 orbifold with transverse A singularity. So basically, so they are just toric Calabi-Yau 3 orbifolds, such that so toric Calabi-Yau 3 orbifolds are obtained by gluing charts of the form C3 mod G. It's like all the charts looks like the case of Zhengyu. It's like C2 mod G and times C. So in this case, Dusty Rose also proved that this result that FGR X plus and X minus are related by analytic continuation and change of variables. And yeah, his result relies on some previous results, which we will describe some later. Now, more recently in 2018, so this is like KP2C3 mod D3. Yeah, I think they took them like, I heard this talk on this result for about 10 years. So it's complete like 3 years ago. So this case is more complicated. It's not transverse AN singularity. So C3 is the action we described earlier. So in this case, you see like FG, you cannot get FG X plus from fgx minus alone. To recover fgx plus, you need to use all the fg prime where g prime is less or equal to g. So they describe this, and there's analytic continuation and change of variable and symplectic transformation. And this symplectic transformation tells you exactly how, after you do the analytic continuation, fg and all this fg prime are related. So what we can do is actually we can prove the same result, but now we can do any k-equivalent toric Calabi-Yau orbifolds related by a single toric word crossing. So now let me turn to the open version. So we will consider open. Yeah, let me do this. Is this okay? So yeah, so the open version. So there's a Brini Cavallari rose. So they also consider this target that Zhengyu considered, but they do the open version. So downstairs you have so x minus is c plus c2 minus vm. So the picture I draw here is actually the case m is equal to 3. So the z1 axis is a stack t c copy of c. So the generic stabilizer of the first coordinate is like vm. After, so the Crepant resolution, the pre-image of the origin is like this 2p1, and the pre-image of, yeah, and then you get this yeah, so then now there are two cases. So suppose that your Agnetti Vafa brain is this red Lagrangian is just a circle times c, and it's not changed. It doesn't change. It doesn't touch the this. It doesn't. It is not changed after the resolution. So in this case, Brini Cavallari rose can show that for this red Lagrangian, then the open generating function of the open Gromov-Witten invariants are related by analytic continuation and change of variables. But then if you consider the purple Lagrangian downstairs, then after the resolution, in this case, you get 3 copies. And in the general case, you get m copies. So, and then, so upstairs, actually, to recover the open Gromov-Witten invariance downstairs relative to this purple Lagrangian, upstairs, you need to count curves with boundary in, can be any of this L1 or L2 or L3. And then, so then they can prove by analytic continuation and change of variable, and some yeah, and some linear transformation, they are the same. So this is like the open version for like this AN transverse singularities. So and for the disk invariant, so there's a result like Q and Joe. So when they have toric Calabi-Yau orbitals, which are k equivalent, such that the Lagrangian is actually smooth, so it's not changed under this Crepant transformation, they can show that the disk generating function is related by analytic continuation and change of variables. And then, so my student, so in 2020, so you can prove that in the general setting where x plus and x minus are toric Calabi-Yau orbitals related by a single wall crossing. And there are two cases. So first, he considered the case where the Lagrangian can be stacky. So of course, still when m is equal to 1, it corresponds to the previous case. So suppose that it's stocky, but it's not changed under this Crepant transformation. Then this generation is related by analytic continuation and change of variables. Now suppose that because we are considering a single wall crossing, so it will in general be a partial resolution where your Lagrangian downstairs can become 2 Lagrangians. And so here, if the generic stabilizer downstairs L minus is like cyclic group of over M, so then you will get like 2 Lagrangians of cyclic groups of order M1 and M2, where M1 plus M2 is M. So recall that in this case, this partition function will be a vector value function. So on the right-hand side, x minus, it will be a column vector with m components. On the left-hand side, for L plus 1, you get m1 components, and for L plus 2, you get m2 components. And then they are related by some linear transformation. So linear transformation, which depends only on M1 and M2 and analytic continuation change of variables. So this is so this is the result in this case. So what we can do is following. We have this result, open Crepant resolution conjecture for any genus. So first, if your Lagrangian can be static but it's not changed under the Crepant resolution, then and then the generating function of like open Gromov-Witten invariant of all genus. So they are related by analytic continuations, change of variable, but also symplectic transformation. So if you want to understand the generating function of the open Gromov-Witten invariance for X plus, such that the domain is like border Riemann surface with G handles and M holes. So what you need to, so there's a finite set of G prime, M prime determined by GM, and you need to use all this F, G prime, M prime for the X minus, and we know how exactly they are related after analytic continuation and change of variables. And suppose that your L is also changed after the partial resolution, you actually get 2 Lagrangians. Then after the resolution, you consider generating function of like open Gromov-Witten invariants for the fixed domain of topological type G and N, such that the boundary can be either in L1 or in L2. Then we also know like how this is related to F, G prime, M prime, where again, this G prime, M prime is in a finite subset determined by Gn. So they are related by analytic continuation and change of variables and symplectic transformation. And also there is this linear transformation, which already shows up in this case. So this is what we can prove. So finally, let me outline our proof. So our proof relies on the remodeling conjecture by Bouchard-Klemm-Marino and Pasquetti. Can be viewed as some version of all genus open and closed mirror symmetry for symplectic toric Calabi-Yau orbifold, exactly the targets that we considered. And it was proving full generality by Fang and Zhong and myself. Well, there's a proof in the smooth case by Chekhov-Eynard-Orantin, but today we want to consider this Crepant transformation conjecture, so we need the orbifold version. So the idea is the following. So if you get, so we have this toric Calabi-Yau orbifold. So we call that the Taylor parameter. There are p Taylor parameters, and then or in the orbifold case, extended Taylor parameters, and we also fix some frame at negative Vafa brane. So from this toric data, we can write down explicitly a spectral curve. So C log X log Y and B. So where C is known as a mirror curve. So it's a very explicit mirror curve. It's very explicit curve in C star 2 defined by some Lorentz theories. And the coefficient depend on key variables. So the number of complex parameters of this mirror curve is equal to the number of extended Taylor parameters, P. And there's also a natural compactification. So here I have this P. So this P is some lattice polygon in the plane. And then this polygon will define a projective toric surface together with a polarization. And then this mirror curve in C star 2 has a natural compactification in this projective toric surface. And then, so log X and log Y, X and Y are just a coordinate on C star 2. And the genus, it turns out the genus of this compactified mirror curve is equal to the dimension of the fourth Chen-Lang cohomology of our toric Calabi-Yau orbifold. And also this B is a meromorphic symmetry 2 form. It's a very classical object. It's the fundamental bidifferential of the second kind. So it has a double pole along it's meromorphic symmetric on the compactified mirror curve has a double pole along the diagonal, holomorphic outside diagonal, and in local holomorphic coordinate, the double pole like this, like 1 over V1 minus V2 squared. But this is not unique if the genus is greater than 0, and you need to normalize it using a symplectic basis by requiring that the period of like alpha cycles are 0. And so then, so the things, once you have this kind of spectral curve, there's a topological recursion, which defines for you from the initial data omega 0,1 and this omega 0,2. So it defines for us omega gn. So it's defined recursively by taking residue of at the 2g minus 2. So here g is the slash g and slash m, because this is not a gn in the generating function. Slash g is the genus of the mirror curve. Slash n is the number of punctures in the uncompactified mirror curve. So these will be meromorphic symmetric M form on this C bar n, and it's holomorphic outside the ramification point. And omega gn can be obtained by omega g1. So the point is the following. So the point is the neural symmetry work like this. So if we have a Lagrangian which is possibly stacky, it will correspond to M. So if the if it's the automorphism to the cyclic of order M, then on the mirror curve it corresponds to exactly M punctures. And we can project it to C star. The projection to C star extend to holomorphic map. And you see downstairs, now we get a small disk, and the map is, so this is not a branch point. So this X are local holomorphic coordinate on the mirror curve for this pink disk center at the punctures. And we can pull back our omega gm because they will be actually holomorphic near these punctures. So we will get this like holomorphic symmetric M form on this M copies of this small pink disk. And in this coordinate, so the coefficient are holomorphic and symmetric function in x1 to xn. It also depends holomorphically in the complex parameter 2. And what we can prove, which is conjecture, is actually after the very explicit closed neural map, the generating function of the genus G Gromov-Witten invariant of F is omega Gn, and then the generating function of open Gromov-Witten invariants Fgn is related to this Wgn in this way under the open and closed neural map. So to prove so now, as a consequence, this formal power series actually is like holomorphic and has a positive radius of convergence. So to relate Fgn and Fg of it remains to relate Fgn omega Gm plus and omega Gm minus. And so the way is we do is the following. For x plus and minus, we choose the basis of second Chen-Lang cohomology such that the first slash G of them form a basis of the compactly supported Chen-Lang cohomology. And we choose a dual basis of the fourth Chen-Lang cohomology. And there is this I function which appears in the work of neural theorem for Pauli stack, such that when you expand it in this basis, we get so these are very explicit formal power hypergeometric PA and WB. And to relate it to the neural curve, it turns out that if you consider the second relative homology of C star to relative to the neural curve, we have a linear isomorphism sending a relative cycle to the relative period of this holomorphic Q form on C star 2. And then, so we choose relative period which maps this Pi and Wi. And then we have, right, so then we have this A cycle and B cycle, which are relative cycle, and they map to the first homology of the uncompactified neural curve. And then also there's an inclusion from the neural curve to the compactified neural curve. It turns out that the image will give us a symplectic basis of the compactified neural curve. And if we use this alpha to normalize the normalize omega 0,2, we will get the neural symmetry. So now the analytic continuation and change of variable and symplectic transform are just determined by this Crepant Transformation Conjecture and this analytic continuation of the solution space or the Gaussman in parallel transport of this relative cycles. And this has been computed before. So under this basis, it's of this form, and then we have this 2G by 2G submatrix, which is actually symplectic. So this gives us a symplectic. This matrix actually determines the symplectic transformation between omega Gm minus and the parallel analytic continuation of omega Gm plus. And we have, in particular, if your G is 0, like in this transverse AN case, then you don't have this, and you just have analytic continuation, change of variable. You don't have symplectic transformation. The omega Gm plus is determined by omega Gm minus. Okay, sorry, I think maybe I'm already over time, so thank you for your attention.
Thank you. Are there any questions?
Yes, I have one. Actually, two. First question, what happens when the marked points flow into, move towards each other and degenerate? Is there any more information that you can get?